so we're finishing up the note sheet. We are finishing it today. I believe we actually finished this problem here because we figured out the values of this one here to be 1/2, -2/3, and 1 plus or minus the square root of 3. So what we're going to start off with this here is x cubed minus 5x squared minus 2x plus 24. And I think as y'all started figuring out, it's going to be very helpful to start with graphing, because if we graph this, clear that out, x cubed minus 5x squared minus 2x plus 24. If we type it in there and graph, it will give us the graph, and we're looking for what values of x will make the y value be 0. We're looking for where it's going to cross the x-axis. We're looking for the values of x that will make the function equal 0. And we see here it does cross the x-axis in 3 points. So if we go second graph, we can look at the table, the input-output values, our x, y values. And looking at this here, when x is -2, the y value is 0. When x is 3, the y value is 0. When x is 4, the y value is 0. So it's telling us that x is -2, 3, and 4. These are the values. The calculator told us these are the values that we have. These are our specific values for this equation here. Now, interestingly enough, because it is a degree 3, we need 3 solutions. Because it's a cubic, it has 3 solutions. So we're done. We are given all 3. We could do the synthetic division at this point to make sure. It won't tell us a whole lot. It won't tell us anything more than we already have. Because one is just going to verify that they are solutions because they give us a remainder of 0. Because we would drop the 1 and do -2 times 1 is -2. -2 plus -5 is going to be -7. -2 times -7 is positive 14. 2 plus -2 plus 14, 12. -2 times 12 is -24. And 24 plus -24 is indeed 0. Let's put that away for now. So again, it didn't tell us anything new. It just told us that -2 is a solution, and we knew it was a solution from the graphing calculator telling us that it's a 0. I could do the same thing with 3. 3 times 1 is 3. -7 plus 3 is -4. 3 times -4 is -12. And 12 plus -12 is, lo and behold, 0. When I go to plug the variables back in, -4 would be our constant term. X would be our, 1 would be our x to the first, telling us that the expression that we need to solve last is x minus 4 equals 0. Telling us that x equals 4. But again, the graphing calculator already told us, it already gave us all this information. So it's really not telling us anything new, because once we have these 3 terms here, we're done. Questions on this here? So really, when we look at an equation like this one here, 3x to the 4th minus 2x cubed minus 37x squared plus 24x plus 12, the best place to start would be to what? Graph it. So I'd go on and plug it in a graphing calculator. I would get the practice with plugging this in, because you are going to have questions like this on the test. So it might be helpful to get used to doing this and not just having to do it on the test. So if we plug this in, we start off with y equals. We're going to clear that out. 3x to the 4th minus 2x x to the third minus 37x squared plus 24x plus 12. So we're going to type the whole thing in and hit graph. Now we do see it crosses 4 times. Since it is a degree 4, we should expect it to cross 4 times or intersect and touch the graph twice or have at least 2. 4 is the most that we can have, so all 4 solutions are listed here. And if we look at the table, the only value that the table gives us directly is 1. Because when x is 1, the y value is 0. We don't care so much that when x is 0, the y value is 12. We want to know what values of x will make this function be 0. So that's telling us that x is indeed equal to 1. But for us to be able to get it to a point where we can solve for the rest, we need at least 2. We need 2 less than the degree. And since the degree is 4, I need at least 2 solutions before we can really continue and use quadratics, our methods for solving quadratics, to finish solving this. So we're going to have to use our rational zeros, where p is the factors of the constant term and q is the factors of the leading coefficient. So our constant term in this case is 12. So the first thing we need to do is get all the factors of 12. 1 and 12, 2 and 6, 3 and 4. So what we're doing is looking for all the numbers that multiply together to give us 12. 1 times 12, 2 times 6, 3 times 4. So we have 1, 2, 3, 4, 6, and 12. Q is the factors of the leading coefficient. Well, the only factors of 3, the only numbers that multiply together to give us 3 is 1 and 3. So questions on any of this so far before we start listing out our factors? I always start with the first value q. I always start with q's factor of 1 first, because we're going to divide every factor of p by 1. Well, when we divide anything by 1, we get that number back. So 1 over 1 is just 1, 2 over 1 is 2, 3 over 1 is 3, 4 over 1 is 4, 6 over 1 is 6, 12 over 1 is 12. So really we can say we're going to list all of those p-values back with plus and minus. Now we're going to move on to the 3, and we're going to say 1 over 3. And 1 over 3 doesn't reduce. It's not been listed already, so we do have plus or minus 1/3. Our next one we're going to have is 2 over 3. 2/3 doesn't reduce. It's not been represented already, so we have positive negative 2/3. Our next setup would be 3 over 3. Well, 3 divided by 3 is 1. 1 is already listed. We don't have it again. 4/3. 4/3 doesn't reduce. It's not been listed, so 4/3 is our next option. Next, we have 6/3. 6 over 3 is going to be 2. It's already listed. And lastly, we have 12 over 3. 12 divided by 3 is 4. It is already listed. So the only solution, possible rational solutions, are these here. And as we look at the graph and look at the table, we can see that the only integer solution that works is positive 1. So negative 1 is out. It doesn't work. Positive negative 2, positive negative 3, positive negative 4, positive negative 6, and positive negative 12 are all gone. They did not show up. They did not cross. The graph did not cross to those spots. So we can throw those values out. We know those don't work. So now we're really looking at 1/3, 2/3, 4/3, negative 1/3, negative 2/3, and negative 4/3. As we saw the other day, we can use the graphing calculator to find these and check these values. Now for us to check them, it is second, trace, enter. Second, trace enter will let us calculate these values. Now the first one we had was 1/3, 1 divided by 3. And we can see here it tells us at the bottom of the screen, our window, that when x is 1/3, the y value is 15.851852. That's not what we want. So we can move on to the negative version of it, negative 1/3. And when the x value is negative 1/3, the y value is 0. So it tells us that our other x value is negative 1/3. Now we can keep going on. We can say 2/3. 2/3 does not give me a y value of 0. Negative 2/3 also does not give me a y value of 0. And lastly, we have 4/3 and negative 4/3. Neither one of those gives us a y value of 0. So we have these two here. Now it is also interesting to look at the graph because our two that we got were the two closer to the middle. The other two values that we have, the other two solutions, one of them is between 1, 2, 3, and 4, and the other is between -1, -2, -3, and -4. So they have to be between -3 and -4, or 3 and 4, yes? Are any of the possible rational zeros anywhere close to being between 3 and 4, or -3 and -4? Well, no, so we can immediately throw them out because they are not in that range. They don't have that value. They're not going to be out there. It's ways to get rid of possible solutions, because if we can find ways to check these values without having to check these values or calculate these values, it makes it easier on us. Now that we did find enough solutions to take it from a quartic down to a quadratic, we're going to do our synthetic division to simplify, to reduce this degree. Now it doesn't matter if we use 1 or -1/3 first, we just have to pick one. And at this point here, if you need to use the calculator, use the calculator, because we can say 3 times -1/3. Because we're doing our -1/3 times 3, and that is -1. Then we add those two numbers together. -2 plus -1 is -3. -1/3 times our -3 is going to give us +1. And when we add -37 plus 1, we get -36. -1/3 times -36 is going to give us a +12. 24 plus 12 is going to give us a +36. And -1/3 times +36 is going to be -12. And 12 plus -12 is indeed 0. Now the other solution value we found was +1. We're going to repeat the process. 1 times 1 gives us make sure. Oh, nope. Brought the 3 down. 1 times 3 is 3. -3 plus 3 is 0. 1 times 0 is 0. -36 plus 0 is -36. 1 times -36 is -36. And 36 plus -36 is 0. And we should expect it to be 0 because both of these are solutions. And what it's done is it's reduced it to a quadratic for us. Our -36 is our constant term. It's the term without a variable. Zeros are linear, our variable to the first power, and the 3 is our quadratic, our variable to the second power. So if we write this expression back out, we get 3x squared minus 36 equals 0. Now this is nicer than the last two that we had to get down to this point. And the biggest reason is that it does not have a middle term. We do not have a x to the first power. Because if we're missing that x to the first power, we can use the square root method. We can get the x squared term by itself and take the square root of both sides. So that means for us here that we can add 36 to both sides, telling us that 3x squared is equal to 36. At this point here, we can divide both sides by 3, telling us x squared is equal to 12. So we had to add 36 and divide by 3 because at this point here, the x squared term is indeed by itself. So the last thing we can do is take the square root of both sides because the square root of x squared is x. And whenever we square root both sides, we add the plus or minus because it could be positive or negative. Now the square root of 12. 30xs is nice enough to simplify it for us, telling us it's 2 square roots of 3, plus or minus 2 square roots of 3. And those are our solutions. I can come back over here to the graphing calculator and tell it to evaluate 2 square roots of 3, and for our case and purpose, 2.7 e to the negative 11 is close enough. And negative 2 square roots of 3 is probably going to tell us it is indeed 0. So negative 3.3 e to the negative 11. And again, e is just 10 to the number after it. So really what we're saying is that this is 1, 2, 3, 4, 7, 8, 9, 10, 11. This is what it's telling us that value is. And realistically for this here, that is 0. Questions on how we solve these here? All right. What we're going to do next. What we have next is the irrational conjugates theorem. The irrational conjugates theorem, the main point to it is that if a plus the square root of b is a solution, if it's a root, a minus the square root of b is also a solution. It is also a root of this here. If we have one, we have to have the other. That's also why 2 square root of 3, since it's a solution, negative 2 square root of 3 has to be a solution. If we have one, we have to have the other. They always come in pairs. It is also the same thing as why we have our complex conjugate theorem. If a plus bi is a solution, then a minus bi is a solution. If we have one, we have to have the other. And we're going to use that to find a polynomial of least degree. What we're given is zeros. Here we're given these two zeros. We want to find the polynomial function, a polynomial function that has these zeros. Now to do this, we're really working backwards. We're told that x is equal to 3, and x is equal to 2 plus the square root of 5. We're told that these are the solutions. We want to find the equation that has these values as solutions. So we do have this here, but we also have a third value. Because of the complex conjugate, or the irrational conjugate theory, it says that if 2 plus the square root of 5 is a solution, well, 2 minus the square root of 5 is a solution. If we have one, we have to have the other. Now we set these up like this here really to find what is the factored form of these values. So to get from a solution to a factored form, what we need to do is get these equations equal to 0. So for our x equals 3, we would minus 3, telling us that the factored form really is x minus 3. X minus 3 is the factor of this higher degree polynomial function. We would do the same thing for our 2 plus the square root of 5. We would start off by subtracting 2 from both sides, telling us that x minus 2 is equal to the square root of 5. Now again, we need to get it equal to 0, so we would also subtract the square root of 5 from both sides. telling us that x minus 2 minus the square root of 5 is 0. And lastly, we're going to do the exact same thing on this one here. We would subtract 2, telling us x minus 2 is equal to negative square root of 5. Then we would add the square root of 5 to both sides, telling us that x minus 2 plus the square root of 5 is our other factored form. So the three factored forms, our three main factors, are x minus 3, x minus 2 minus the square root of 5, and x minus 2 plus the square root of 5. So the next main thing we're going to need to do is actually multiply these two together. Now, it is perfectly possible to multiply the x minus 3 and x minus 2 minus the square root of 5. I would not do that. I would multiply our complex conjugates together, or our irrational conjugates together first. So when we're multiplying this together, the first thing we're going to do is distribute the x. X times x is going to be x squared. X times negative 2 is going to be negative 2x. X times the square root of 5 is going to be plus x square roots of 5. Then we're going to do the same thing with negative 2. Negative 2 times x is negative 2x. Negative 2 times negative 2 is going to be plus 4. And negative 2 times the square root of 5 is negative 2 square roots of 5. And lastly, distributing negative square root of 5. Negative square root of 5 times x is negative x square roots of 5. Negative square root of 5 times negative 2, the negative and negative make a plus, giving us 2 square roots of 5. And lastly, negative square root of 5 times the square root of 5. Our negative times a positive is a negative. Square root of 5 times the square root of 5. Well, 5 times 5, we can multiply what's inside because they are like radicals, giving us the square root of 25, which is just 5. Or we could say that it's the square root of 5 squared because it's multiplied by itself, which is still just 5. Now, we still have a lot of terms here. I want to look at a few in particular first. One of them is x squared of 5 and negative x squared of 5. Those are like terms because they both have x in the radical. Well, what is x squared of 5 minus x squared of 5? 0. They are like terms, they're opposite signs because I have one of them and I have a negative version of it. So really we have 1 minus 1, which is 0. Negative 2 square root of 5 and positive 2 square roots of 5. Those also become 0. Do we have any radical terms left? No, that's the main reason we do it first, so that we don't have any radicals left. Now we combine the rest of our like terms. X squared doesn't have any. Negative 2x minus 2x is negative 4x. And then we have 4 minus 5 is negative 1. Last but not least, we do this one more time. X times x squared is x cubed. X times negative 4x is negative 4x squared. X times negative 1 is negative x. We're also going to distribute the negative 3. Negative 3 times x squared is negative 3x squared. Negative 3 times negative 4x is going to be plus 12x. And negative 3 times negative 1 is plus 3. To finish this up, we're going to combine like terms. Well, x cubed doesn't have any. Negative 4x squared minus 3x squared is negative 7x squared. Negative x plus 12x would be plus 11x. And our constant term of 3 does not have any like terms. telling us x cubed minus 7x squared plus 11x plus 3 is our polynomial of least degree and leading coefficient of 1. Questions on this here? Not too bad, lots of steps, just working backwards. Because it's almost like we were trying to factor it to get to the solutions, but they gave us the solution first. We're working it in reverse. Questions on this here? All right. We're going to do one more. X equals 0, x equals 5, x equals negative 5, and x equals 5, and x equals negative 5 plus the square root of 8. So, on this here, we need to set them all equal to 0. Now, we do have the first three. There is one more. We also have negative 5 minus the square root of 8, because if we have one, we have to have the other. So throw that on the floor. Now, once we get them all set up, we get all four, we need to get each one of these equal to 0. Now, luckily for us, x equals 0 is already done. Now, the x equals 5, we would have to subtract 5, telling me that x minus 5 is equal to 0. For our next one, we would add 5. Telling us that x plus 5 is equal to the square root of 8 minus square root of 8 from both sides. Telling us that x plus 5 minus square root of 8 is going to be our next factor. Then our last one, we would do almost the same thing. We would start out by adding 5 to both sides, but instead of subtracting the square root of 8, we have to add. And I think if you notice, our factored form of our conjugates is just almost the conjugates, flipping the sign in front of the radical. So really, we could get both of those at once if we wanted to, by just figuring out what the first one is, and then just changing the sign in front of the radical. For complex conjugates, we could just change the sign in front of I. Questions on this so far? Now, for the most part, we've done one multiplication at a time. Because if we said this here, we can only multiply x and x minus 5, or our x plus 5 minus the square root of 8 and x plus 5 plus the square root of 8. We can only do that at a time. And that is true. I can't just multiply x through all three. That does not work because there's only one of them. But what we can do is I can multiply these two together. Well, x times x is x squared. X times negative 5 is negative 5x. That's fine. But I can also multiply these two together at the same time, because we're not distributing something over multiple. We're not misaligning it, misgrouping it. We're just doing two separate multiplications at the same time. Now our x times x is x squared. X times 5 is going to be plus 5x. X times the square root of 8 is going to be plus x square roots of 8. Then we'll do the same thing with our positive 5. 5 times x is plus 5x. 5 times 5 is plus 25. 5 times the square root of 8 is plus 5 square roots of 8. And lastly, negative square root of 8, we're going to distribute it Negative square root of 8 times x is negative x square roots of 8. Negative square root of 8 times 5 is negative 5 square roots of 8. And negative square root of 8 times the square root of 8 well, that's just 8. Better. Because the square root of 8 times the square root of 8 would be the square root of 64, which is just 8. Or we could say it's the square root of 8 squared because it's being multiplied by itself. Square and square cancel, still just 8. Now, x squared minus 5 is as simplified as it gets because neither one of those are like terms. X square root of 8 and negative x square root of 8 will cancel. 5 square root of 8 and negative 5 square root of 8 cancel. Those all become 0. X squared is the only term. It's only like term. Our x terms, we have 5x plus 5x, which is plus 10x. And lastly, we have 25 minus 8, which is going to be plus 17. Now that brings us to our last multiplication. We just have to do it one more time, and then we are finished with this here. First thing we can distribute is the x squared. Now x squared times x squared would indeed be x to the 4th. X squared times 10x is going to be plus 10x cubed. And x squared times 17 is going to be plus 17x squared. And lastly, we can distribute the negative 5. Negative 5 times x squared is negative 5x cubed. Negative 5x times 10x is negative 50 x squared. And negative 5x times 17 is going to be negative 85x. Again, the calculations, negative 5 times 17, we can do in the calculator. We don't have to do that by hand. And lastly, we're going to combine like terms. X to the 4th does not have any like terms. 10x cubed and negative 5x cubed are like terms, and they'll simplify to positive 5x cubed. 17x squared minus 50x squared would be negative 33x squared. And 85x does not have any like terms. So telling us that our polynomial is x to the 4th plus 5x cubed minus 33x squared minus 85 would be the solution for this here. Oh, so the x equals 0? So since it told us that the solution is 0, we just said x equal to 0. Yes. So that does guarantee us that we won't have a constant term because we do have that x equals 0. And if it shows up twice, we actually won't have an x squared term either. Or we won't have a constant term. If 0 shows up twice, we won't have an x term. 3 times x squared, it kind of simplifies down. But